Welcome to my channel. Again, this is your favorite tutor, Yomi Omorewa. Welcome to PaySector Tutorial. If you are new on my channel, kindly subscribe and click the notification bell so you will be notified whenever I upload any new video on the channel. Uh, this very morning or afternoon, we're looking at limits and differentiation. Limits and differentiation. Just a while ago, you could check it on my channel. I was teaching trigonometry and I took time to explain the trigonometry because I'll be needing the knowledge of what we did a while ago in what we are having now, which is the limits and differentiation. So you're welcome. Let's go to what we have. Now we talk about limits. Actually, limits is just talking about the value of a function approaching some input. And basically, limits is used in derivatives, is used for integral, is used for continuity. So you hear something like limit as x approaches infinity, limit as x approaches or is getting to so and so. So we're going to be demonstrating that. But the first thing I like to look at in limits is the property of limits. The properties of limits. In the limit, I'm not going to be looking at everything because I actually dealt with limits in my book that I'm writing called I'm writing a book on calculus, and I've dealt with limits severely on it. In fact, I'd finished limits on it completely. I dealt severely on it. So I will just pick few properties from limit. And number one property I like to consider is that limits, which usually we normally use it like this, lim. As x tends to infinity, your 1 over x is 0. Is a property. Number two, limits. As you have this, as x tends to 0 or approaches 0, your this is 1. You have 1 here. Number three, you have limits. As this, you have this to be also equals to 1. Number four, you also have limits that's tan x over x is giving you 1. I'm sure that's very clear. Now, basically, I may have to add maybe limit as x tends to a. You have and then by the time you are opening this, it gives you limit as x tends to a, this plus minus limit as x tends to a g of x. Okay, so that's those are the few properties of limits I might have to consider, just very few. But you might be wondering, why stand like this, stand x over x? Maybe you're not familiar with this, and then you are wondering, why is this one having x down, and because x is not having x down, and this is having x. Now you need to know something. There's what we call even function and odd function. Now, let me summarize what this even function is. A function is said to be even if you have a case like this. That's a function is said to be even. Okay, I'm starting with even function. When you have a case like this, where the minus sign does not reflect here, an example of even function, actually, you have x squared, you have x4, you have cos x, you have sec x, and so on and so forth. All these are classic example of an even function. Okay, so like you have something like this now. Okay, I was trying to demonstrate something. I I think there will be no need for that. Okay. So then talking about an odd function. For an odd function, you have this. A good example, x cubed, sine x, your cosec x, your tan x. All these are good examples. So you can now see why your sine x cannot exhibit the same property as your cos x. The reason is because one is an even function and while the other is an odd function. Okay, I'm sure that's very clear now to you. The next thing I like to explain is the fact that there are methods of evaluating limits. There are methods of evaluating limit. When you're evaluating limit, there are, number one, we have what we call direct substitution. For example, if you have limits now, you are given a question. Let's say you are given a question, limit as s equals to 1. And then you are asked to evaluate this. Direct substitution means that where you have x, you just put x. You remember what will happen here now? Okay, so let me not use you put 1 here. That's 1 square is 1. 1 minus 1, that's what? That's 0. And then 2 times 1, that's 2. And that will give you 0 divided by 2, and that's 0. Okay, so this is called direct substitution. You putting in the value of x directly, put it here, you have this. That's direct substitution. Number 2, we have what we call by factorization. By factorization, you have a situation like this. Limits, let's say as x tends to 2, you have this. Yes, limit as x tends to 2. You have a situation like this. Limit as x tends to 2. You are asked to evaluate this. Evaluate this as limit as x tends to 2. Remember, you cannot use direct substitution here. Let me explain this now. Why can you not use it? Why can't we do direct substitution? If you were to confront average secondary school students or 100-level students, and you ask them that, oh, solve this question, if there are people who do not have the knowledge of what we're talking about, they could just put 2 here. So 2 here means 2 squared, that's 4. 4 minus 4, that's 0. Put 2 here, that's 0 up, 0 down. And then you ask an average secondary school student who do not understand certain thing, it tells you that 0 divided by 0 is equals to 0. But is that true? That is not true. 0 divided by 0 is not 0. Okay, you know that. 0 divided by 0 is indeterminate. It's undefined. Okay? And because you have to avoid 0 divided by 0 because it's indeterminate or undefined, then that takes us to another method. So what do I do here? Since I cannot do direct substitution, then this is difference of 2 squared, which means I have to do it this way. Okay, so cancel this, cancel this. So in place now, you can now put, in place of x, put 2 here, and then put 2 here, you have 4. So the answer is now 4. We use factorization method and we got it. Number 3, rationalization. Now, there are limits that we have to rationalize. Let me give you an example. Evaluate limit as x tends to 0. Imagine this again. A limit like this, you cannot do direct substitution. Again, let me say it again. If you were to do direct substitution, it means that you're going to put 0 here. So cos 0, what will that give you? 1, because cos 0 is 1, right? and this is 1, right? Okay, so 1 minus 1, that's 0. And then you put 0 here, 0 divided by 0 is still indeterminate form. So we cannot use the method. That's why we're having different method. Now, and you cannot use factorization method either. How are you going to factorize? What are you going to factorize here? There's nothing to factorize. And so you have to use another method called rationalization method, okay? And so how do we go about this? To use rationalization method is just to come here, limit, so multiply the conjugate of the denominator, the conjugate, look at it. If here were to be minus plus before, this place will be minus. So let's multiply. If you multiply this by this, we call it difference of 2 squared. But we have to simplify it calmly. 1 times 1, that's 1. 1 times this, that's cos x. This times this, that's minus this. Minus times plus, that's minus. Cos times cos, that's cos squares x. Then x times this, so we have x 1 plus cos x. Limit as x tends to 0. It's alright. So I'm sure as I'm being systematic about it, you're following. Okay, so we have limit as x tends to 0. We have 1. This, we cancel this. So you have minus cos square x over x, 1 plus this. This is what you have. Recall that is equals to 1 this from trigonometry that we did earlier. So what do I have here? I have sine square x over x, 1 bracket cos x. So limit as x tends to 0, sine x over x, limit as x tends to 0, sine x over this. You can see the way I'm applying the limit. Okay. Remember, limit as x tends to 0. What is sine x over x? What did I say the other time? From the property of limit is 1. Can you see now? Times sine 0. 1 plus cos 0. 1 times 0. 1 plus 1. That is 0 divided by 2. That is 0. So our answer is 0. Now, you should note something carefully, that when you have, okay, maybe I will talk about that later. I'll talk about that. So 0 divided by 2, our answer is 0. So I've been able to evaluate this now, this limit, using rationalization method, and you can see what I'm getting at the end of the day. I'm sure that is very, very easy and very simple and straightforward as well. I like to look at one more method. That method is called L'Hopital rule. L'Hopital rule. Now, you're going to appreciate this rule because of it almost look like your, what you call mighty formula or formula method in quadratic equation. Okay, look at L'Hopital rule. What does the rule say? The rule says, for example, look at it now, you have limit. I'm going to use it to solve the question we have solved earlier so that you appreciate what the rule can do. We solved this question the other time, and what did we get? We got, I think it was 4. Yes, it was 4 we got. Now, L'Hopital rule says that when you are given a question that will lead to indeterminate form or undefined, now you have to differentiate. When you differentiate the first time, substitute the value you are given. Will it lead to indeterminate form? If it will lead to indeterminate form, differentiate it again. Will it lead to indeterminate form? Differentiate it. That is, you have to differentiate until you can ascertain that it will not give you an indeterminate form or undefined expression. That is when you stop. Okay, in this case now we have not even differentiated yet, but if we substitute the value of x, it will lead to indeterminate form. So what do? I will differentiate. Differentiating x squared, it will give me 2x, and then differentiating constant, that's 0. Differentiating x, that's 1. Differentiating 2, that's 0. So I have 2x divided by 1, that's 2x. And what is that? What is x? Remember, x is 2. So 2x multiplied by 2, and that's 4. Exactly what we got when we're using factorization method. We got the same thing. When we're using factorization method, we got 4. And now we just used L'Hopital rule and we got the same 4. This is a beautiful method. Now, let's use it to solve the question we just finished now. So evaluate lim as x tends to 0, 1 cos x over x. So using it now differentiate this. Now you have 0. Differentiate cos x, you have minus sine x. Differentiate x now, you have 1. So this will give you x. Sine 0, what do you have? 0. Exactly. This is shorter. You remember when we were solving just now, it took us some time. Look at it. We had to solve till we got to this place. But just with 2-3 lines, we got exactly the same thing. 0, 0. That's L'Hopital rule. What did I do here? Simply, I differentiated this, I differentiated it, I differentiated this. And then at the end of the day, I substituted the value of x into this, and then sine 0 is 0. Sine 90 is 1, but sine 0 is 0. Cos 0 is 1, and cos 90 is 0. And I'm sure that's very clear. That's the method. Although we still have perturbation method, we still have the one you have to divide by the highest variable, blah, 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 not degree of this, about 6-7 method. But I have decided to use 4 method to explain the limits. Now, when evaluating limit, you must endeavor to avoid the following. Some of them are infinity divided by infinity, infinity dot infinity, a constant divided by 0, and so on and so forth. So in other words, if you say a number, you can also say divide the 0 divided by 0, avoid the 2. Now imagine 2 divided by 0. 2 divided by 0 is not 0, please. It is not 0. But 0 divided by 2 is 0. 2 divided by 0, you must avoid it because it will lead to undefined expression. If it's an undefined expression or indeterminate form. So we must avoid that when evaluating limits. Okay? I think that is all for that. That is all. That takes me to differentiation. I'll just use some minutes to touch on few methods of differentiation. But before then, I like to solve first principle. In differentiation, our formula says that you have this. So my dy dx in differentiation is this, is n, and this divided by this. N, this. So it means that if I have something like this, using the formula above, the 6 comes down, and then the 6 minus 1, that's 5. That's the answer. If I have something like this now, and then my dy dx, what happened to it? The 3 comes down, 3 minus 1, that's 2. But this is not called first principle. This is simply your general formula. But I'm going to use first principle to solve this and see what will happen. First principle, I will use it to do it. So let's see what will happen if I use first principle. Remember, when I did it now, it was just one line. I was done with the answer. But with first principle, let's see what will happen. So first principle, you have s cubed. So step 1, apply change in y to this, and then you have x here, apply change in x to this. So that's step 1. Step 2, minus y from both sides. So y goes, so you have change in y equals to x plus change in x, and then your y. What's your y? Go back to this, you have this. So that's it. The next step is to expand this, to open up this. And in opening up this, I want to show you something. Remember, this is what I'm solving, just one line, we got it. But I want to show you what I'm to do now to expand. I do not know if you have heard of Pascal triangle. Pascal triangle, where you have your number and you have your coefficients, like you have this now. You have 1, you have 1, 1. Okay, let's say number, and let's say coefficients. And then you have 2, you write 1, 1 plus 1, 2, you have 1 again. You have 3, you put 1, 1 plus 2, 3, 2 plus 1, 3, and then you write 1. You come to 4, that's 1 again, that's 4, that's 6, that's 4, and 1. So you can keep going. Let me stop at 5. You have 1, that's 5, that's 10, that's 10, that's 5, and 1. So you can see it becomes a triangle. And that's what we call Pascal triangle. So I'm going to be doing that now. So Pascal triangle, this is raised to power 3. And if it's raised to power 3, it means that this is the one I'm using, this coefficient. So I'm going to have this now. Carefully open this bracket. This is 3 raised to power 3. And this is changing s raised to power 0. The coefficient that follows now is 3, so you write 3. X will be decreasing now 2, and changing x will come up 1, because by the time you add, it's still 3. The next coefficient is 3, so you have 3, then x, then changing x or 2, and then the last one 1, so you don't need to write that. Then x0, then changing s raised to power 3. So that's what you have there. So with this now, you have s raised to power 3, you have 3s squared, you have this, you have 3x change in s all squared, and then you have change in s all raised to power what? 3. What's the next thing? Divide both sides by change in x. So change in y over change in x is equals to this. So you have this. Now, so changing y over changing x. Oh, I'm so sorry. I did not finish my work. I was still having this here, which I did not cancel. So cancel, cancel, changing y. I left it actually. I'm so sorry, it was an oversight. So you cannot divide both sides by change in x. So changing y over changing x. So 3s squared changing x plus 3s change in this plus change in s3 all in changing y. So you have this. If you divide it by this now, you have 3s squared. If you divide it by this is square, please. It will be left with 1. This will go, one of it will go. If you divide it by this, you have just square that will be left. So here you say limits as change in x is tending to 0, so my change in y over change in x will metamorphose into dy dx. So I have my dy dx is equals to 3x squared, 3x 0 squared. So you have 3x squared as my final answer, because this 0, this 0. So you could see now that it took us a whole page for us to finish what we could have just solved using one line. So that's what first principle can cause. And this is pretty simple. I'm going to solve the one that you cannot even make use of, Pascal triangle. You have to make use of binomial expansion. You have to use binomial expansion. Let me explain. Imagine you are given something like this now. If you find dy dx of this will come down, and then half minus 1, that's minus half. And this could have been the answer, or you could solve further and say, okay, and then because of the 2 here, you have 2 here. So this becomes the answer. But now, the situation is that we can use first principle to solve this. And let's use first principle and see. Remember, it was just one line I used, and look at what I got. Now I want to use first principle to solve this and see if I'm going to get this or not. So let's go. So using first principle, apply change in y as usual. And then next, minus y from both sides as usual as well. What's your y? Our y is this. So you could say now, but you need to know binomial expansion, because we cannot use Pascal triangle for this. That's the limitation of Pascal triangle, because this is a fractional stuff, something, and being a fractional thing, Pascal triangle is limited. Okay, it's not a whole number. So if it's a whole number, we would have looked at the coefficients, number, and then, but now we're having fraction. So we need to think of binomial expansion. Binomial expansion, I mean something like this. That when you have something like this in binomial expansion, okay. So from binomial expansion, so this is the same thing as nx and n minus 1 over 2 factorial s squared. So I could continue like that, okay. I could, if I were to do another one, it will now be n, I open bracket, n minus 1, close bracket, n minus 2, close bracket, over 3 factorial. 3 factorial simply means 3 times 2 times 1. Okay, 4 factorial means 4 times 3 times 2 times 1. Okay, so now we are solving this. So I'll quickly do this now. Okay. Okay, so looking at this now, what's the next thing? So I will have to now come, since this does not look like this, because we don't have one here, I have to work on this. So I have to work on this. That's mathematics for you, but it's quite simple. Do not think, oh, what's all this? This is too hard. Okay, mathematics is quite interesting. So now you have this. I'll factorize x out. So the one will come out 1. And then this can become change in x over x. Yes, I'll explain that. Yes. And then this will come. The half can come this way, and then you have the half this way. Now let me explain this. X times 1, that's x. X times change in x, it will not be x change in x. So if you divide x, you are left with change in x. So if I open this, exactly what we have here. So in this case now, we have gotten our 1. You can see now, it now look like this. But in this case now, our n is half. So compare it. If you compare it with this now, your n here is your half. Your x here is your change in x over this. So bearing that in mind, so let's expand as we have it here. Okay, let me do it this way. Let's expand. Let's expand. So expanding it, we have, so what's the first thing? 1. What's the next thing? N. And what's our n here? Half. Multiplied by x. What's our x here? Change in x over x. What's the next thing there? N, which is half. What's the next thing again? N minus 1 over what? 2 factorial multiplied by x squared. What's our x here? Change in x over x. Always to power 2. You could continue like that. And then remember that there is a minus here. So if I decide to open, to close here, so there's another minus half here, which is this now. Please take note of that. So you have change in this. So let's open this up. We have 1, open here up. You have a change in x over 2x. Come here, minus half. Plus times minus, how do I know? Because half minus 1 is minus half, right? Yes, minus half. Let me show you here. Half, this is the half now. Inside here, half minus 1 is minus half. The 2 factorial is 1 over 2. So 1 times 1 times 1 times 1 here, and then you have change in s here. So change in s squared here. Then 2 times 2 times 2 times 2, that's 8. Multiplied by s here. So s here is s squared. So you have s squared there. And then you have plus plus, you can't, minus your x half here. I'm leaving something behind. I am leaving something behind, sorry. And I'm trying to get, let me go back to where I'm coming from. Oh, I've seen it. I've seen what I'm leaving behind. Yes, I've seen it from here. From here. So, I wouldn't want to go back again. Yeah, what I did here, this half is affecting this. So let me open something up here for you. Why? Because of this app, it will open up. Okay, so okay, sorry about that. So this time is this when you open the bracket, so you have change in x. Then you multiply this by this, open the bracket too. So you have change in x over 2x, x half. You come here again, the same thing. you have change in x, so and then minus change in x. So this go. Okay, so you have this change in x over 2x x half, then we have x half change in x over 8x squared. Oh, this is beautiful. So the next thing is to divide both sides by change in x. So we are dividing both sides by changing x. Okay, so dividing both sides by changing x, what do you have now? You have changing y over changing x equal 1 over changing x, all brackets, then you have yes, so you have it this way. So change in y, so when you divide this by this, what will you have? You have change in x over 2x. And then when you divide this by this, you have change in x1 will be left, and then you have, so limits as change in x tends to 0, y so my dy dx is equals to this. Okay, so this is where we'll be wrapping up everything today. So everything here is 0. Because this times this divided by this, everything is 0. So you have this left. So therefore, my dy dx is equals to x over 2x. Now, from the law of indices, this is the same thing as 2. This is 1, it goes up, so it's half. And this is the same thing as exactly the same thing I got, the same thing as the question I solved earlier. That was just one line, but look at this one. How many lines? So this is so interesting. Now, before I go, I'd like you to know that I could go into what we call uh, product rule now, which says that if y is equals to uv, dy dx is u dv dx plus v du dx, and then we start solving question. I could go to quotient rule, which says that if y equals to u over v, dy dx equals to v du dx minus u dv dx over v squared. And I could continue going to chain rule, which you have your dy dx equals to dy du dot du dx. I could go to implicit function, something like this. You have x squared, you have y squared equals to this, and then you multiply, you differentiate, and then you switch here. If you have to differentiate this now with respect to it, you become 2y dy dx. That's implicit function.
I could go on into parametric equation and begin to solve. I could go to logarithmic equation. I could go to exponential equation. I could go to hyperbola equation, that's inverse function. I could go on like that till I get to application of differentiation, which are minimum, maximum, and plot point of inflection. I could go into rates. I could go into velocity and acceleration. I could go to other application, equation of tangent and normal to the curve. So there are so many things to still cover under the topic, but we're going to cut the curtain here today. I remain my humble self, Yomi Omorewa. Bye.